So now we'll see what is ionic radius. As you know, what is ionic radius? It is definitely the sum of ionic radii of cation and anion, which gives the distance between ions in a crystal lattice. Okay, so it is the distance between, or we can say like, yeah, ionic radii of cation and anion, and the sum of both gives the distance between the ions in crystal lattice. Usually, this is like expressed in picometer. Then the point is when an atom loses an electron, it becomes cation. Definitely, if that electron is no longer dealing with or no longer do not have any kind of contributions to shielding on other electrons or nothing like that, so the size decreases. And if an atom gain to form an anion, the size will be increasing. These things are actually generally Then coordination number also with increasing coordination number at ionic radii also increases. Now coming to this example, this is nothing but the example use of sodium halides and the silver halides. So what is the net outcome of this point is from fluorine to bromine, the ionic radii increases, right? That is, fluorine is the most smallest or say most electronegative atom, and as from fluorine to bromine, size increases. As a result, ionic radii also increases. In cation is the same for all. The anion only is the only reason for the change. Now, ion in high spin. So, for a particular ion, it can exist in either high spin or low spin. So, the existence in high spin state gives the large ionic radii than in low spin. Okay. And this is the general conclusion. Now, the distance between two ions, that is the ionic radii, is experimentally determined using X-ray crystallography. And that gives the side length of unit cells in crystal also. So when we consider this NaCl, the length of each edge of unit cell is 564. So each edge of unit cell is considered to be arranged as sodium, chlorine, sodium. So that is the, yes, the chlorine is from the sodium, chlorine, and sodium. So edge is twice the NaCl separation. 1, 2, 2 hexana. So the distance will be the half. The ionic radii will be the half of the length of edge of unit cell. Okay. Now, according to Landy determined ionic radii by taking a case where cation is too small compared to anion. Anion is very big. Cation is too small, like lithium iodide. Okay. So, in case of lithium iodide, lithium is too small, right? And this lithium get fits into the hole within the crystal lattice. Also, as you know, lithium is too small. The both iodine ions in the corners can touch each other because it is too small to sit in this cavity. So the iodine ions are touching each other. That is, the distance between neighboring iodides is in crystal is assumed to be twice their radius of iodine, right? From distance. Okay, when we see the distance, you can actually like okay, imagine the thing. Two iodine ions are kept in touching each other, definitely the radius will be the twice the radius of a iodine, right? Yes, so that is in lithium iodide, distance between two neighboring is 214 picometer, which means the estimated rate. So we can use this particular radii of lithium iodide to estimate, say, rubidium iodide. So in case of rubidium iodide, we know the inter-ionic distance to be 356. And you know 214 is the distance between two neighboring iodine ions. So, inter-ionic distance in rubidium iodine is 356, which means 142 will be the ionic radii. How this is found is that you know the ionic radii of lithium. Sorry, iodine. In lithium iodide, you know that of lithium. So when we subtract this and this, you get 142. Okay. This is used as a standard, like a standard, and we use this. This is what Landy did. Now the other, oh sorry. So this is the thing. And the other thing is Pauling. Pauling used the effective nuclear charge to proportion distance between ions into anionic and cationic. Okay. So then comes the radius ratio rule. So radius ratio rule is as the size of cation increases, more anions of particular size can pack around it. Uh, so thus knowing the size of ion, we should be able to predict prior which type of crystal packing will be observed. That is the radius ratio rule. That is the significance of this radius ratio rule. Also, other than this, Pauling and Landay, other one scientists estimated this by considering the relative volume of ions. Okay, relative volume of ions determined by, from electrical polarizability. By using the measurements of refractive index and all, ionic radii is estimated. That is by relative volume, considering the relative volume of ions and uh, relative volume of ions is determined from electrical polarizability. So here comes the radius ratio rule that, as I said, as the cation become larger, okay, a more number of anions can pack around it. Okay. Therefore, by knowing the size of ion, you should be able to predict the crystal structure, crystal packing, the type of crystal packing. In an ideal ionic crystal, coordination number is determined by electrostatic conservation. So, cation around themselves with many anions as possible and vice versa. So, this is a radius ratio rule. That is, the rho is R plus by R minus. Okay. This is the radius ratio rule. This is the basic concept of radius ratio rule. Then comes the limiting radius ratio rule. Limiting radius ratio rule means minimum allowable value for ratio of ionic radii for a structure to be stable. So, according to radius ratio rule, you are able to predict the structure or crystal packing, the type of crystal packing possible. And by using this limiting radius ratio, we will be able to find limiting means minimum, okay? Minimum allowable value for ratio of ionic radii for a structure to be stable, to get a very stable, very good structure, which is the minimum number of minimum allowable value for the ratio of ionic radii. That is this ratio. You know, according to radius ratio rule, R plus by R minus. So this is the radius ratio rule. So this particular ratio is minimum value of rho for a structure to be stable. And the conclusion is this: if the cation and anion are of large difference in size, they are unstable. The most stable thing is the cation and anion should be having a considerably same size. That is the more good or more acceptable concept.